If you're looking for a quick but effective explanation of Dijkstra's algorithm where you don't have to think too hard, congrats, you're in the right place. In this video, I'll give you a rough idea of how it works and do a quick example. This is an algorithm to find the shortest path between two nodes. Shortest meaning minimal distance, and distance meaning the numbers on the edges. Here's the algorithm in 4 sentences. You have a beginning node, an end node, and all the nodes in between. You start at the beginning node and explore outward, looking at edges and keeping track of the distances from the beginning node to every other node. When you find a shorter path to a node, you update the distance to that node from the beginning node. Once you've explored the whole graph, you can look at your table to find out what the shortest path is. Here's the example. We want to get from A to D. We'll start with A and look at each edge connected to A. We always look at the edge with the shortest distance first. In this case, it's A to B, which has distance 1. Let's make a table to keep track of all of this. It'll have 3 columns: the node, the shortest known distance from A to that node, and the node right before it in that path. If that's a lot to digest, don't worry, it'll make sense soon. From A to B is 1. That means a few things for B. First, we have a path from A to B. That path's distance is 1. In that path, the node right before B is A, because we just started and the path is only 2 nodes long. Next edge. From A to C is 2. We now have a path from A to C, so the shortest known distance from A to C is now 2. The node before C in that path is A. From A to D is 7. So for D, the shortest distance is 7. The node before D in that path is also A. That's all of A's neighbors, so we can consider A visited. To make things easier, we'll keep a list of visited nodes. For the next node to visit, let's look at our table and pick the unvisited node with the shortest distance from A. Right now, that's B. B only has 1 unvisited edge. From B to D is 2. Notice how we found a new path to D. The shortest distance was 7 when the shortest known path was from A to D, but we found a new path that's shorter. Going from A to B to D is only a distance of 3. So we update our table. The shortest distance is now 3, and the node right before D in that path is B. Now B is visited. C has the next shortest distance from A on our table, so let's visit C. C also only has 1 unvisited edge. From C to D is 2. We have a new path from A to D through C, but its distance is 4, which is more than the current shortest distance for D. So we disregard it. That's all of C's edges, so we mark it as visited. D is the only unvisited node, so let's visit it. Since D has no unvisited edges, we mark D as visited. Since that's all the nodes and edges, we're done with the table. To see what the shortest path is from A to D, we start with D's row and look at the previous node, which is B. Then we go to B and look at B's previous node, which is A. Rinse and repeat until you get to the beginning node. In this case, A is the beginning node, so we're done. The shortest path is A, B, D, with a distance of 3. This is a small example, but these steps work for any size graph. And that's it. If you found this video helpful, toss it a like. If you want to see more, hit subscribe. Thanks for watching.